Hello everyone, welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll. Today we're going to be continuing on the theme that we already started in the last video. We talked about the idea of fields, quantum fields in particular, and this is such a deep and rich topic it's going to take more than one video to get through all of what's interesting about quantum field theory. In fact, in the last video, really all we did was establish that if you had free fields, that is to say fields that didn't interact with each other or even themselves, then you could think of them as collections of particles. Today, we're going to take the next obvious step and let them interact with each other. So today's big idea is interactions. And the way to do that is, of course, like many of these videos, I have the title and then I have what I really want to talk about. What I'm really talking about today are Fineman diagrams and how we use Fineman diagrams to calculate the interactions between quantum fields, thought of as collections of particles. So to remember where we are, we have classical field configurations. Let's try to make that prettier, okay? Classical fields, which is our starting point, have a configuration. And we just started with the simplest case of a scalar field. Scalar field meaning just that at every point in space, there is a real number, a value for that field. More complicated examples would be vectors or tensors or spinors or whatever. And then we quantize it, okay? So we get a quantum wave function. And that is just an assignment to every possible field configuration of some complex number. So this is not phi at x, but the configuration of phi for all x's gets a complex number, capital psi. That is the amplitude for that particular field configuration. So you might have, in just a simple one-dimensional example, if this is space x, and this is the value of our field phi, you have some configuration, and you call that phi1 of x. And the wave function assigns a complex number called the amplitude, psi of phi1, to that particular configuration. You have some other configuration over here. This is all, when I say over here, I mean over here on the pad that I'm writing on, not there in space. All these configurations are hypothetical possible configurations of the field in space. So here's another configuration you could have, call that phi2. And in the quantum theory, you would have an amplitude for that being the actual field configuration. And then you measure it, you observe the field everywhere somehow, and the probability of observing some particular field configuration phi is just the wave function for phi absolute value squared. That's the Born rule for quantum field theory. Good. So that's a big abstract mess, and we needed to learn how to sort of make some sense of it, to turn it into something useful. And what we did was to show that in this simple spherical cow world, where we had free fields not interacting with each other, we could first decompose them into modes, that is to say, into collections of plane waves of field configurations that are just sine waves all throughout space with a certain direction they're moving in, a certain wavelength. And then we could treat each mode one by one. And a wonderful, spectacularly helpful thing happened. Each mode behaves like a simple harmonic oscillator. We know how to deal with simple harmonic oscillators. So in particular, simple harmonic oscillators have a lowest energy state, a next highest energy state, a next highest energy state, and so forth. And it turns out that we can interpret this formalism in the case of the modes of a quantum field as corresponding to 0 particle states, 1 particle states, 2 particle states, and so forth. So we have modes of a field, and we could write those as phi sub k. K is the wave vector. It tells you the wavelength and the direction that the field is moving in. As a function of h, the height. So very roughly speaking, you have some sine wave here. This is x, this is phi, k. And the wavelength, which is the distance between, let's say, two troughs, lambda, is 2 pi over the size of k. And the height is just this tiny value here, h, the amplitude of the highest peak in the sine wave. And so we showed that modes of a field are like simple harmonic oscillators. Of course, there are an infinite number of modes, so that's an infinite number of simple harmonic oscillators vibrating all throughout space. And we can quantize a simple harmonic oscillator, solve the Schrödinger equation one by one, and we find that there are energy levels equally spaced. And then we interpret those energy levels as collections of particles. So at the end of the day, a quantum field is just an organizational tool. I shouldn't say just. Is an organizational tool for talking about many collections of particles, and in fact, collections, superpositions of different numbers of particles. I should also say that this is in the spherical Cal regime where the field is non-interacting. Things become a little bit more complicated when they interact a little bit. We're going to ignore all those complications. But when the fields interact by a lot, or the fields do something dramatic, this description in terms of particles might be completely off base. There are absolutely situations in which the fieldiness of the quantum field really does matter, that it's not just a cheap substitute for thinking about particles. Hopefully we'll get a chance to talk about some of those situations later on. Okay. So real fields, I don't mean the real numbers, I mean actual fields in the world, are not free. That is to say, they do interact. So we have to sort of turn on the interactions a little bit. Just like Galileo could drop a ball and say, well, let's ignore air resistance and put it in later. We're starting with free fields and then we're putting in interactions later. So, in fact, what happens is that particles, we can still think of them as particles. This is the wonderful thing about field theory. Even when we turn on the interactions, we can still think of them as particles. They scatter. I'm not going to write all this down. They scatter ... They can scatter off each other. They can annihilate. They can decay, right? A neutron decays into a proton, an electron, an antineutrino. They can create other particles, annihilate, and so forth. They can recombine. So we want to invent some way of thinking about this. We made a huge step by going from quantum fields to particles, but we want to do the next step. So what does that involve? So here's what we should be thinking about. The nice thing, as I hinted at, if you hear some scratching in the background, I think that's Caliban. He's a little bit excited this time of day. The thing that we can do is not only think of the free fields as particles, but continue to think of them as particles even when we turn on interactions. The difference is, unlike ordinary non-field theory quantum mechanics, the number of particles is not a conserved quantity. The wave function of the quantum field is a superposition, like I said, of different numbers of particles, and the Schrödinger equation that tells you how that wave function evolves can change the number of particles through different kinds of interactions. So we want a way of dealing with that, but nevertheless, we're going to deal with it by thinking of it as particles, okay? We've sort of used the fieldness to justify that we can think of it as particles. For the rest of this lecture, it's particles all the way down. I keep calling them lectures. They're videos. They're nice, informal videos. They're not lectures. Don't be intimidated. Okay, so what we're thinking of is a collection of particles, and we start by imagining the particles are unentangled. So despite all of the hoopla about saying that there's only one wave function of the universe, we start by saying that there are two different particles, let's say, if we're doing a scattering experiment, two different particles that have their own wave functions. So here is particle 1 with its wave function, it's traveling this way. Here's particle 2, its wave function traveling that way. And this, under the Schrödinger equation, is going to evolve into, I'm going to draw it bigger because it's going to be more fun, lots of little particles going out in all different directions, right? These little blobs I'm drawing are supposed to be little wave packets. A wave packet is just a little bit of wave function that is sort of localized to one region of space. And you can make these wave packets, as we said, even by superimposing plane waves that stretch all over space. That's kind of the fun thing about the Fourier transform. You can get a localized function by summing up a bunch of functions that are certainly not localized. Okay, so this is the transition through time between, let's say, two particles coming in, scattering out, and this picture on the left is perfectly sensible. We start with two different particles, unentangled, they have their own wave functions. The picture on the right is entirely suggestive and not very sensible, because after, we're going to have a situation where there's a lot of entanglement. It's not going to be that crucial, but it's there. But more importantly, it will be a superposition of all sorts of different numbers of particles. So it will not look anything like this nice, neat thing where you have just a certain collection of wave packets that are all separate from each other. The individual components of the wave function will look that way. So that's what we're going to do. We're going to sort of do it chance by chance, right? You have two particles coming in. Let's analyze the idea that they scatter into two particles, scatter into three particles, scatter into four particles, etc. But how do you actually calculate that? And, I'm going to give you sort of a half-baked explanation of this. By the end, you will not actually be able to calculate anything at all, but you will know how the calculations are done, at least half of the ideas behind them. So if you ever want to pick up a book on quantum field theory, you'll be very prepared conceptually to follow what's going on. And it was, of course, Richard Feynman who figured out the way that we all do this in the brilliant idea of Fineman diagrams. And Fineman diagrams, you've all seen them, right? The little pictures, little cartoon stick figures of particles coming together. But one thing to emphasize here is that they're not just pictures. You might think, if you didn't go too deeply into what's going on here, that the Fineman diagrams are just representations of things that can happen. The two electrons can scatter off of each other by exchanging a photon. But they're much more than that. Every Fineman diagram is a number. It is a way of calculating a number, and that number is a contribution to the amplitude, to the quantum mechanical wave function for that set of particles that are going out of the Fineman diagram. So the initial particles in the Fineman diagram represent a starting wave function. The outgoing particles represent a contribution to the final wave function. And Feynman gave us a recipe. He didn't just say this was a good idea to think about. He actually told us how to do it. So he said that that we can think of some basic set of interactions. So by an interaction, I mean, let's say an electron can absorb a photon. That's an example of an interaction. And then we combine them in all possible ways. So if you start with some idea that you're going to ask, well, how can an electron and a positron, which is an anti-electron, how can they scatter off of each other to form just another electron and positron, not change their identity, just, scatter off of each other in some way? Well, by starting with that fundamental interaction of photons and electrons, we'll see in a second, there's a lot of different ways to combine them to get that final interaction. And Feynman says, do them all. Combine them all. This is quantum mechanics. Everything that can happen is going to contribute to what's going on. In the back of his mind, he was inventing the path integral formulation of quantum mechanics, where literally, if you're just doing point particles, every trajectory the particle can take will contribute to the final answer. That was sort of an inspiration for Fineman diagrams, but you don't need to know anything about the path integral way of doing quantum mechanics to do Fineman diagrams. It's much more straightforward than that. And then you calculate the number using this combination, the amplitude. And you know what to do with the amplitude. When someone hands you a quantum mechanical amplitude, the probability of whatever final state you're considering is that amplitude for that final state squared. So I write this over and over again because I really do want to emphasize this fact I already mentioned, that quantum field theory is not a replacement for quantum mechanics. It's a specific example of quantum mechanics. All the rules of quantum mechanics are still here in quantum field theory. It's just the thing we're quantizing are fields, not particles. Okay, so here's an example. The example I just mentioned. Let's think about an electron and a positron. Remember that Paul Dirac taught us that there's things called antiparticles. So an electron is a tiny particle with a negative charge, and a positron is a tiny particle with a positive charge, which is the antiparticle of the electron. But because the electron was discovered first and is more important for our lives, we write the electron as E minus. It is the electron with a negative charge. The positron we don't write as P because P is for proton. We write the positron as E plus. It's the antiparticle of the electron. We're going to take an electron and positron and ask that they scatter into an electron and another positron. So they don't change their identity, they just maybe change their momentum. They literally bump into each other. Now this is not the only thing that can happen. You're not done, okay? You would also like to calculate the probability that this electron and positron do everything else that they can do. And we will have a way of doing that. But for right now, we're focusing on this particular final state so we can find the probability of that. And roughly, schematically, before we get into the details, the picture is we have time running left to right. So again, different ways of thinking about physics conventionally choose different ways for time to run. In relativity, in space-time, time runs from bottom to top. In particle physics, sometimes it does that, but more often it goes left to right. And there are studies, I mentioned Lera Bereditzky, people who are Hebrew readers or other people who read right to left sometimes make it go right to left. So we will do left to right, because that is my culture that I come from. And we start with an electron and a positron, and we draw lines representing these particles moving through time. And then stuff happens, okay? So this is a blob that I'm going to label stuff happens, and we'll be a little bit more specific about that in a second. And then out emerge another electron and a positron. And I say another one because they need not, in principle, be the same ones. There's, in some sense, no such thing as the same ones. These electrons and positrons are vibrations in the underlying electron and positron field, so they need not have any personal identity over time, okay? But this is the kind of interaction that we want to think about. We want to know, how do we actually calculate numbers for this? Okay, well, Feynman gave us the rule. He says we start with some basic set of interactions. For this process, when we do this scattering, we're going to do it in the context of quantum electrodynamics, okay? QED, as it is called, quantum electrodynamics. That is, Feynman wrote a nice little book about it at a semi-popular level that you can pick up in stores. It is the first really successful full-blown interacting quantum field theory. It was the center of focus for people like Feynman and Schwinger and Tominaga when they were thinking about renormalization and interactions and all that stuff. And it's the theory of just electrons, positrons, and photons. So it's electrons and positrons interacting with themselves and with each other, but only through electromagnetism. So we're not worried about the weak nuclear force or gravity or anything like that, okay? So in that context, we have one fundamental interaction. And sometimes, because we're in Fineman diagram land, we talk about interactions as vertices. So the vertex in quantum electrodynamics is an electron comes in, positron comes in, and they hit each other, and a photon comes out. Photons are, for historical reasons, in particle physics, photons are labeled gamma. Okay, so this is a photon. So here's the interaction, and there's one more little notational thing that happens, which is that there is a feature of electrons and positrons that there is a certain amount of electronness which is conserved, okay, in quantum electrodynamics. In other theories, it's not. But in QED, the electrons are neither created or destroyed. What they can do is travel backwards in time. So this is the famous idea of Feynman that he popularized it. He got it from someone else whose name I'm forgetting right now. But the idea that you can think of antiparticles as particles traveling backwards in time. And of course, it's only a matter of our human prejudice that we label electrons particles and positrons antiparticles. The point is that they are antiparticles of each other. It's just as fair to say the electron is an antiparticle of a positron as it is the other way around. But we are full of electrons, so we, give privilege to the electrons. So we draw a little arrow on the line to represent the direction in which the electronness is moving. And because the positron can be thought of as an electron going backward in time, we draw the arrow backward, okay? So you got to get this straight. The particles are moving from left to right. The electronness for the electron is therefore moving left to right, but because the positron can be thought of as an electron going backward in time, the electronness is going right to left in the case of the positron, okay? So these arrows do not represent the direction of motion of the particles. They represent the flow of this quantity called electronness, which, by the way, no one ever uses the word electronness, but it's the closest you'll get is something called fermion number. And we'll talk about what that means, but electrons are fermion number +1, positrons are fermion number -1. Okay, and this is the fundamental interaction from which we will build all of our quantum electrodynamics diagrams. And the final piece of information you need to know is, like I said, there is a number attached to this. You use these pictures to calculate the amplitude. And the number that is attached to this vertex is the square root of alpha. Alpha is the fine structure constant. And you'll see why it's a square root in a second. The fine structure constant is just a way of thinking about how strong the electromagnetic interaction is, right? It's a dimensionless number. Alpha is approximately 1 over 137. There was a time when people thought maybe it was exactly 1 over 137 and tried to explain that using numerology. That didn't work because it's not exactly 137. But the number 137 still holds a precious place in the minds of particle physicists. So the fine structure constant is a small number. It's less than 1%, right? It tells us how strong the electromagnetic interaction is, and every one of these vertices gets a factor of the square root of alpha. So one thing to keep in mind here is that this is reassuring to us, the fact that alpha is small, because we're thinking of these interactions as tiny perturbations on top of the spherical cow of the free field theory. If the interactions were really, really strong, you couldn't do that, right? Putting on the interactions would change everything in a dramatic way. The fact that alpha is small is what lets us get away with this way of thinking about interactions in quantum field theories. Okay. And there is one rule you need to know. The rule is you can flip particles, lines of particles, let's say. These lines are called the propagators, but we won't get into that detail. The lines that we're drawing on the Fineman diagrams, that's all you need to know. We can flip the lines between in and out. So if a particle is coming in and it's electron, and that we have a certain diagram we can draw, then we know there is another diagram where the particle's coming out. And we just flipped it, literally sort of moving it over. The arrow now changes the direction in which it's moving. So by interchanging particles with antiparticles. So what that means is, we drew this diagram with an electron and a positron coming in, a photon coming out. We said that's associated with the number alpha. So particles go to antiparticles means E minus gets interchanged with E plus. Electrons become positrons and vice versa. The photon, in this way of thinking, is its own antiparticle. So photons just remain photons. There's no electric charge that would have to change sign. Photons are neutral particles. So they're just their own antiparticles in this way of thinking. And therefore, this diagram, let me shrink you down a little bit here. This diagram implies the existence of a couple of other diagrams. It implies the existence of a diagram where an electron comes in, and we take that positron line and move it over from coming in to going out, and therefore we get a photon going out, gamma, and guess what? Another electron coming out. So this is another diagram, another interaction, where rather than two particles, positron, electron, coming in and annihilating into a photon, we have an electron just spitting out a photon. But it's the same Fineman diagram status. So this diagram also comes with the square root of alpha associated with it. And likewise, we can flip both particles, both electron and positron on the other side, and make the photon come in. And these go into E minus, E plus, okay? Also associated with the factor, a numerical factor of square root of alpha, and so forth. And you can do other things as well. Once you get inside the middle of more complicated Fineman diagrams, there's a lot of different things that you can imagine doing. Okay. So, I mean, that's already kind of nice, right? It's kind of a little bit of a unification in some sense. This is saying that there's something happening, something that could happen, called the annihilation of an electron and a positron into a photon. There's a certain number, the fine structure constant, that tells us how likely that is. There's a completely different sounding thing, which is the photon can be given off by an electron or by a positron equally well, and that also is characterized by the same number. And this is why at the Fineman diagram level, because they're just the same Fineman diagram, flipping some particles from past to future. Because remember, time is going this way in all these pictures. Okay, so let's put it all together then. We want to calculate an electron and a positron going into a photon. No, sorry, that's not what we want to calculate. We want to calculate these going into another electron and positron. Okay, so how can we do that? Well, Feynman says basic set of interactions, that's what we got. Combine them in all possible ways. Okay, so given that we want to start with E minus E plus, we have E minus E plus. They go into this, what can they possibly do? All they can do is do that fundamental interaction that we drew, right? That's the only thing that we can start with in this picture. I can be prettier than that. And then they turn into a photon, but the photon isn't what we want coming out. We want an electron and a positron, but guess what? The photon can spit out an electron and positron. So here's our arrows, E minus E plus. Okay, and that's a photon in the middle. This vertex gets a factor of alpha. This vertex gets a factor of alpha. So there's a number associated with this diagram, which is approximately alpha, the fine structure constant. That's why it's the square root of alpha, because historically things like this are what happened. And so we use alpha to characterize this. By the way, when we square it to get a probability, it'll be alpha squared anyway. So this is a process that contributes, and it gives a number. We can calculate the probability that the electron and the positron will scatter off of each other. There are other factors that matter, right? The fact that if you have an electron and positron far away, they're less likely to scatter than an electron and positron very nearby. That comes into other details that I'm just not worrying about right now, so-called kinematic factors. What is the position and the momentum, etc., of the wave packets coming in? But this is the fundamental quantum field theory-ness of the calculation. But it's actually not the only thing that can contribute, right? Because I said the only thing the electron and positron can do is emit a photon, but there is another... Yeah, I'm realizing that was a complete and total lie now that I say it out loud, now that I think about it. It is true that the electron has to sort of emit a photon. The electron cannot sort of directly interact with the positron without emitting a photon, but there's another way to draw that, which is this. E minus, E plus, okay. The electron comes in and it emits a photon. The positron comes in and it absorbs the photon. Look at that. I'm sure all the particle physicists in the audience were laughing at me when I said there's only one way to draw the first one. This is, oops, backwards. This is another perfectly good diagram, also of order alpha, right? The same size, roughly speaking, as a contribution to the final amplitude. And we would add them together. This is, in fact, an example of quantum interference. These diagrams have a typical size of order alpha, the fine structure constant, but I didn't tell you whether they're positive or negative, or they could even be, imaginary components. They're complex numbers in general. All of quantum mechanics is about complex amplitudes. Remember in the Q&A video for quantum mechanics, we talked about the double slit experiment and the fact that it's a crucial feature of quantum mechanics, that the wave function is not just a probability distribution. It can have positive and negative values, and it can interfere, and that sort of makes us think the wave function is a real physical thing. This is still quantum mechanics we're doing. These are contributions to the wave function. We will add them together and then square to get the probability of what's happening. And these can interfere with each other, and that interference has been observed in experiments. All the Fineman diagrams give you separate contributions. You have to add them up, and they can cancel out to give 0. There are situations where there's a certain kind of process that you would think could happen if you just drew one Fineman diagram, but it doesn't actually happen because all the diagrams just cancel out, and you get 0 at the end of the day. So it's still quantum mechanics. There can be interference. The other thing to say is to go back, I said that this is not the only thing that can happen, right? So there's another process. There's also processes like this fun one where an electron and a positron come in and you go like this. So you have 2 photons coming out, and the electronness goes this way, comes out that way, okay? So this is a different process. This is not E minus E plus goes to E minus E plus. This is E minus E plus goes to 2 photons. It's another thing that can happen. You would not add this to the previous Fineman diagrams because it's contributing to a different final state. Just like in the double slit experiment, the interference happens at every point on the detector. You add up what the contributions are there. You don't add up contributions at different points of the detector. You add up contributions to the same final state. So these 2 diagrams contribute to the same final state, an electron and a positron. This diagram and ones like it contribute to different final states. So they're there, but there's different processes. We don't have to go into them right now. Okay, so in fact, let me just get rid of these because they're there. I didn't want you to think that we were done, but let's continue on with this particular process. We're not done. Even now drawing, you might think, all right, think about it, well, this looks like all the diagrams we can draw. Not true. There are an infinite number of diagrams we can draw. So in fact, there's an infinite series. And that kind of becomes important. The infinite series is because, so let's draw it this way. We have, just very schematically, we have this blob that represents stuff happening, okay? And what we're saying is there's a contribution that looks like this. Once you get good at the Fineman diagrams, you stop drawing the arrows and the labels with E- and E+. You can also label these individual lines, these propagators, with their momentum and their energy. These are properties that they have, but you just keep those in mind implicitly. You can stop drawing them. So there's a diagram like this. And there's another diagram that we drew that looks like this, okay? But there's also diagrams, let me see what I chose to draw. Here's a diagram with 2 photons going back and forth. And of course, once you realize that, then you realize there's an arbitrary number of photons. That's clearly going to be an infinite number of diagrams. Like I could put 3 photons, 4 photons, 5 photons. It doesn't stop in any way. But there's also different kinds of diagrams. Here's a diagram where the electron-positron annihilate into a photon. Then the photon creates an electron and a positron, but they reannihilate into a photon, and then they go off. Right? That contributes to the final answer. There's one where the electron and positron come in, annihilate to a photon, but another photon gets exchanged between them before they annihilate, and then they go off. And then, as you can imagine, they become more and more complicated. So this seems like bad news. This seems like, oh my goodness, we're trying to do some simple calculation. There's an infinite number of things I have to calculate, and that sounds bad. But in fact, that's not bad. Remember, alpha is approximately 1 over 137, so relatively tiny number. And every one of these vertices comes with a square root of alpha. So the more vertices you get, like something here, you have, let's colorize it. Something like this diagram, you have 1, 2, 3, 4 vertices, as opposed to over here you only have 2, right? So you will, in fact, get more and more an infinite number of diagrams, but only more and more complicated diagrams. We've drawn all the simple diagrams already. And as the diagrams become more and more complicated, this diagram looks like alpha, this one looks like alpha, but this one looks like alpha squared, as does this alpha squared. Alpha squared, and higher order diagrams will look like alpha cubed, alpha fourth, etc. Because alpha is less than 1, as you raise it to higher and higher powers, you get a smaller and smaller number. So the hope with Fineman diagrams, which will be partially realized, or it'll be exactly realized but in a complicated, non-trivial way, the hope is that even though there's an infinite number of diagrams, these diagrams become less and less important. And in fact, in practice, you don't have to calculate an infinite number of diagrams. You have to calculate the small number of important ones to get an answer that is really, really good. It becomes harder and harder to calculate the diagrams as they get bigger and bigger. I'm leaving out a lot of details about what you actually have to do to calculate them, but you get the basic scaling going on here. So this is an example of perturbation theory, which I mentioned before. Perturbation theory in action. Perturbation theory is the idea that you can start with something you understand perfectly, like free fields or a ball falling without any air resistance. Then you can add in tiny effects and add them as perturbations. So the reason why that works is because they generally, in perturbation theory more generally, not just in this context, you get an infinite power series. By power series, I mean, so you get an infinite series. An infinite series, let's say A for the amplitude we're looking at, can be written as A0 plus A1 plus A2 plus ... where an is proportional to alpha. It's terrible that the proportionality sign looks like an alpha. So I'm going to say some other number epsilon to the power n, some small number epsilon. Epsilon is less than 1. So this general feature is that all of the terms in the series are smaller than the previous terms because they're proportional to epsilon to some power, and epsilon is a small number. You might worry. You might say, well, proportional to covers a great deal of sins. Maybe the constant of proportionality is really big for some term later on. And actually, that's just a legit worry. You should worry about that. I'm not going to poo-poo that. In practice, if you're dealing with well-behaved systems, perturbation theory works very well. Ignoring powers of epsilon to the 1000th power is a pretty good approximation. But you have to be careful. Things can go wrong. Things can be subtle. But this is the thing that most particle physicists learn to do when they learn their quantum field theory. Of course, the other thing that can happen is, so this feature here, that you're a power series in a small number, means that your interactions are weak. And now, what I mean is, by weak, I mean not very strong. Physicists love to use the same words in different contexts to mean different things. So there is an interaction in particle physics that we'll talk about later called the weak nuclear force. It's a dumb name for an important interaction. So sometimes when you say weakly interacting particles, like the dark matter candidates weakly interacting massive particles, what you mean is particles that are interacting through the weak nuclear force. Other times, like here, all you mean is particles that are interacting through some interaction that is not that strong. Okay, so this is just an interaction that is feeble, and when interactions are feeble, perturbation theory works. Not always true. In the so-called strong nuclear force, guess what? The interactions are not weak. They're not even feeble. They are strong. The thing that you might think is a parameter, the thing that plays the role of alpha in the strong nuclear force, can be greater than 1. And if this epsilon here in this power series were greater than 1, this power series would be useless. Every term would be bigger than the previous term, and they would never add up to some finite number. So it's not always true that perturbation theory works, but it's a very good approximation for a lot of very important problems. Certainly for QED, for quantum electrodynamics, it works very well. Okay. So let's do a little bit more digging into the details here. So I said that this fundamental interaction in QED was proportional to the square root of alpha. Says who? Like who invented that rule, right? Well, I'll tell you how. It was, the rules were invented by Feynman, but they are ways of expressing rules that were already invented. So Fineman diagrams are a calculational tool for dealing with quantum field theory. So Feynman did not invent quantum field theory, but he figured out how to work with it in a plausible way, in a way that everyone could do. And, there's the joke that he tells, like when he was first scribbling these diagrams, he was immensely amused by the idea that if his idea panned out, the physics journals would now be full of these little scribbles. And indeed, the first time that he scribbled these things on a blackboard at a seminar, he got made merciless fun of. And now you open any physics journal and it's full of Fineman diagrams. So the rules, where does it come from? How do we assign numbers to vertices, to interactions? Well, even though we're doing quantum mechanics, it's still physics. So remember we did for classical mechanics, we talked about the Newtonian paradigm with F equals ma, but then we also talked about the Hamiltonian way of doing things, where you have phase space and Hamilton's equations. And we also talked about the principle of least action, where you had some integral of some quantity over time, and the minimum of that action, that integral, was the actual physical thing that you did. The actual physical path that a real particle would take. So another thing that Feynman figured out is that you can, and this goes back to the path integral formalism, is that you can do quantum mechanics with an action. But rather than saying, here's an action that is an integral over all of time, and the minimum value of the action is the real one, in quantum mechanics, they're all real, but they don't all count the same. The minimum value of the action is the one that will add up to the biggest contribution to the quantum amplitude, but they're all there in some sense. Quantum mechanics takes advantage of all the different trajectories the system can take. So it turns out, for completely other reasons, that if you're going to invent new laws of physics, that not new laws of physics, but a model for physics that you don't yet understand, it is way simpler, more convenient to work with an action than it is to write down the equivalent of Newton's laws, to write down the equations of motion for the fields, to write down the equivalent of Maxwell's equations. The reason, I'll tell you the reason is because these fields often have symmetries. We'll get into that later. But the symmetries matter a lot, and it is way easier to implement the symmetries in the context of writing down an action than it is in the context of writing down individual equations of motion. And that goes back to the feature that we mentioned earlier about these alternatives to Newtonian mechanics, which is that they're often either in the action formalism or in the Hamiltonian formalism. They're written down in terms of a single function, the action, the Hamiltonian. You don't have to guess separately the equations of motion for every field. You can write down one action, and all of the field's equations of motion come from that one object. So we're going to go back to the action in this particular way of doing things. It will look classical, but we will use it in a quantum mechanical way. So the principle of least action says that we have an action S, and there's an integral of kinetic energy of your particle or your system more generally, minus the potential energy. And then you integrate that over time, dt. So remember, integrals are sums, so we're saying at every moment you evaluate this quantity, kinetic minus potential, you add them all up over all the different moments of time. Now, the fact that you take this quantity and you integrate it over time is always true, so we often just forget the fact that we are integrating it over time. Again, that's implicit in our background knowledge, and we deal directly with this quantity, which is called the Lagrangian. The Lagrangian is just the kinetic energy minus potential energy. It's the thing you integrate over time to get the action. So you can write down S equals something, but it's much more common to write down L equals something. So S equals the integral of L dt. Okay, that's a nice way of saying what we want to do to invent our new theory is to invent the Lagrangian for that theory. Okay, so this is true in the context of particles moving in potentials and things like that, but the same idea is true for fields, but fields are a little bit more complicated, right? They're spread out all over space. There could be different kinds of fields, they could be vectors, etc. So as you might expect, the Lagrangian for fields is in principle a little bit more complicated, but not that much. So for fields, the Lagrangian L can be thought of as the kinetic energy minus something called the gradient energy. We mentioned this before. The kinetic energy is the field changing over time. The gradient energy is the field's profile over space. But we're not done yet. There is still minus the potential energy. So this is saying that in some theories of physics, the value of the field itself contains energy. When the field has zero value, maybe it's zero energy, maybe not, but maybe. When the field is some large value, that contains energy. That's the potential. The potential is not the derivative of anything. That's what makes it the potential. Then also, since we have more than one field in our game, we have an interaction energy. So if you have electrons and photons, for example, in quantum field theory, they are both described by fields, and there better be a term in your Lagrangian that tells how those fields interact with each other. And that's what this term is. So the game that is played by particle physicists the world over is to write down different Lagrangians for different theories of fields interacting in different ways. Now they do have one more big simplification: locality. Locality in this sense means that two fields interact with each other, two different fields or the same field in itself, only when they are at exactly the same point in space. So two fields far away might interact with each other indirectly, like the Earth can interact, and the Earth is made of fields in quantum field theory, so is everything else. So is the sun made of quantum fields. They can interact with each other through gravity, but only because there's a gravitational field in between. In some very strict sense, the Earth interacts with the gravitational field locally, so does the sun, and that interacts back and all the way over in between. So the way that locality manifests itself in this language is that the Lagrangian for a quantum field is an integral over space of something which we call the Lagrange density. And the Lagrange density is a function of the field phi and its derivatives. Oops, can't spell anymore. I'll just say the derivatives. I'm not going to try to notationalize that. Integrated over all of space. So this curly L is the Lagrange density. Density is just something that we have at every point in space, and then we integrate it over everything to get a whole quantity, right? If you have energy density that exists at a point in space, the energy in a volume is the integral of the energy density over that whole volume. The Lagrange density exists at every point in space, and we integrate over all of space to get the total value of the Lagrangian. So this d3x is representing an infinitesimally tiny cube in space, okay? dx, dy, dz. That's what the notation d3x means. And this is just an underappreciated fact about quantum field theory. So it doesn't need to be this. In fact, let me be a little bit more clear here. Let me notice something here. Well, it didn't quite work, but close enough. The fields are functions of x, right? So the field is phi at the point x. So when you're integrating over space, both the fields and their derivatives have a value at every point. And what this is saying is one field at point x interacts with other fields at point x, not at point y. So it is not, for example, we could imagine taking, phi of x, phi 1 of x, and a different field, phi 2 of y, and integrating d3x, d3y. So we integrate twice over space and have fields all over the place interacting with each other. That would be spooky action at a distance, right? That would not be local. That would be bad. So let's just put a big X through that. That's not what we do. This way of writing the Lagrangian for a quantum field theory is just an enormously important feature of reality. The laws of physics didn't have to be that way. They didn't have to be local. We talked in the video about space, about the interesting fact that there's this thing called space in which interactions are local. Why is that? No one knows why, but we know that it's true. And so in quantum field theory, we take advantage of that. In quantum gravity, it might not be true. This is why I keep emphasizing this, because I'm trying to teach you ways that, eventually you're going to grow up to be Nobel Prize winners who quantize gravity. There's indications in quantum gravity that locality is not as important as it is in quantum field theory. But right now we're doing quantum field theory where locality is absolutely 100% central. Okay, so because the action is always the integral over time of the Lagrangian, and the Lagrangian is always the integral over space of the Lagrange density, the thing that particle physicists actually spend their time doing is inventing Lagrange densities, okay? And it's from the Lagrange density that we will get our rule for the Fineman diagrams. So the QFT recipe, quantum field theory, what do you do if you want to be a grown-up quantum field theorist? First, you invent a set of free fields, and you write down their, kinetic energy, gradient energy, and potential energy, right? That's an easy enough thing to do. And then, you have the different kinds of fields, maybe. Then you decide what symmetries the fields have. Can't go into this in detail right now. Need a whole nother video to talk about symmetries, but symmetries turn out to be super duper important in quantum field theory, whether or not it's things like gauge invariance, which is a feature of electromagnetism and the nuclear forces, or just position invariance, time translation invariance, all these things. Symmetries will restrict the different number of terms you can write down in your interaction Lagrangian. And then, that's what you do. You construct an interaction Lagrangian. That is the thing that we indicated will exist. Oh, by the way, yet another abuse of Lagrangian. Yeah, I got it right. Another abuse of language, because the Lagrangian is always the integral of Lagrange density. Not only do field theorists, particle physicists worry about Lagrange densities, they get tired of saying the word density over and over again. So they will often refer to this curly L thing, the thing that you integrate over all of space to get the Lagrangian, as the Lagrangian. So I will do that too. So curly L is really Lagrange density, but we call it the Lagrangian, okay? So this term here, interaction energy, is the interaction Lagrangian, okay? The thing that we will integrate over space to get the actual Lagrangian. So for example, we already have an example of one interaction. An electron, a positron, and a photon can interact with each other in a certain way. So we write LQED. It's the interaction Lagrangian for quantum electrodynamics. And I should pause to mention that in a real quantum field theory textbook, they will spend pages and pages of introducing new notation and a lot of Greek letters and things like that. I've already used a bunch of Greek letters myself, but I'm trying to keep it as straightforward as possible, so my notation is different. But roughly speaking, it is a number, the square root of alpha. Again, I'm hiding some 4 pi's and things like that, times the electron field, times the positron field, times the photon field. So this is the electron, this is the positron, this is the photon. These E's have nothing to do with 2.7, the Euler's constant. Gamma has nothing to do with, there's another constant, the Euler-Mascheroni constant. I'm not going to pronounce it correctly, but these are fields. This is E minus of x is the electron field. Gamma, in this very, very simplified notation, is the photon field. And likewise for the positron field. The reason why I'm sort of slyly smiling and saying that it's a simplified notation is the real photon field is a vector, so it has indices, it has directions, and it's gauge invariant, and there's a whole number of things you need to think about. The real electron field and the positron fields are spinors, and they have their antiparticles, and there are more indices you have to worry about. But forget about all that. We don't need to worry about that. What matters is there's a term in the Lagrangian that has an electron field hitting a photon field and a positron field, and together from them you get the interaction. So this is the rule. This is literally called the Fineman Rules. Given this interaction Lagrangian, you get that this particular diagram, E minus E plus gamma, gets the number square root of alpha. The existence of a term in the Lagrangian with an electron field, a positron field, and a photon field times a number means that there is a Fineman diagram with those 3 particles. And the size of that Fineman diagram, that interaction, that vertex, is the number, whatever that number is. In this case, it happens to be the square root of the fine structure constant. And so this is the game that you play as a professional particle physicist. You invent different Lagrange densities for different fields with different symmetries and so forth. Okay, so you can see, I hope you can see the basic outline. I wonder how small I can actually shrink this. Yeah, you can see the basic outline. Well, look, we've done a lot of stuff. How awesome are we? But there's a lot of details. Okay, and what I want to do is, rather than focusing on computational details right now, I want to give you one little conceptual detail to close things off. A Fineman diagram. This is a point about what is actually physically going on when you look at a Fineman diagram. It's a story. And it's not even an especially accurate story. Fineman diagrams are a way of calculating something that is very rigorous and well-defined. The amplitude for the wave function of the quantum fields to have to be a certain number in a certain final state that you care about. But the steps along the way have a different kind of status. So, by the way, there's one thing I should have said. I realized a while ago. So when I wrote this diagram here, you notice that for some of these diagrams, or for this diagram, for this diagram, I wasn't very careful about whether the photon was going from left to right or right to left. That's because you actually it doesn't matter, really, is what matters, because the photon is its own antiparticle, so whether it's going forward in time or backward in time doesn't matter. Likewise, when we draw, I erased, that's why I can't find it, because I erased it. Remember we drew, let me draw it again. We drew this picture. So here's an electron going in with a positron and creating 2 photons. Gamma, gamma. I also didn't care too much about how to draw that intermediate line, whether it's going forward or backward in time. I just do it vertically. And there you think it might matter because it's an electron or a positron or both. Well, that's the thing. It can be either one. It doesn't matter because the electron and positron are the same things in some sense. Just one is going backward in time, one's going forward in time. But it's the same kind of fieldiness. And I should also mention yet another digression is many of you have heard of this idea called Wheeler's one-electron universe. John Wheeler, who was the PhD thesis advisor for Richard Feynman, as well as the PhD thesis advisor for Hugh Everett, and also for Kip Thorne and a bunch of other famous physicists. So the story goes that one day Feynman gets a phone call from Wheeler, and Wheeler says, I think I know why every electron in the universe has the same mass and charge. And Feynman says, it's 3 a.m, what are you doing? And Wheeler says, it's because they're all the same electron. This is closely related to this idea that in a diagram like this, there's only one line for the electron that is both representing the electron and the positron, right? The idea of Wheeler was that the electron goes forward in time, then it occasionally goes backward in time, and then it goes forward in time. And if you drew the Feynman diagram for the whole universe, there would only be one electron going back and forth in some complicated zigzag. So many of you have heard that. Some of you have heard that theory. Probably fewer of you have heard it is wrong. That is not correct, that theory. So a lot of people sometimes ask me, like, whatever happened to that theory? Why don't people talk about that? It's wrong, and we know it's wrong. It was a very clever idea. Not all clever ideas turn out to be right. The reason why every electron has the same mass and charge as every other electron is because they're all very vibrations, perturbations in the same underlying quantum field, okay? We already knew the answer to that question. Why are all the electrons the same mass and charge? They're the same quantum field, vibrating in different ways. Furthermore, we now know that electrons are not forever. Electrons can turn into other particles under the right circumstances, like muons and stuff like that. So it is just not true that there's only one electron all throughout the universe. There are quantum fields. But in the Fineman diagram, an electron going one way in time is the same as a positron going the other way in time. Therefore, in these intermediate lines, it doesn't matter. Okay, that's what I wanted to say. But that's not what I wanted to say. That was a digression that got me away from what I wanted to say. Let me make this diagram bigger. I can just reuse this diagram. Maybe I can make it bigger. Nope, I can't. Style. Nope, can't make it bigger. All right, I need a bigger diagram, so I'm going to redraw it. Just want to make everything clear here. Here's a Feynman diagram. Electron, positron, 2 photons. By the way, yet another thing. There's a lot going on in Feynman diagrams, so I keep forgetting things that I wanted to say. Why not this one? Why not just consider E minus E plus to a single photon as a physical process? This certainly exists as a diagram, right? It's the fundamental Lego building block that we use to make all of our other diagrams, but we don't consider the process of an electron and a positron annihilating into just one photon. Why not? So I'll give you 10 seconds to see if you can think of the reason why not. We can think of an electron and positron annihilating into 2 photons, but not 1 photon. The answer is that momentum is conserved. Okay, so this electron and a positron, they're massive particles. They're moving more slowly than the speed of light. They have a total net momentum for the 2-particle system, and that total net momentum could be in its rest frame, or it could be whatever, but it's certainly moving slower than the speed of light, right? The center of mass of an electron and a positron is always going to move slower than the speed of light, whereas the photon can move only at the speed of light. So you cannot have a situation where an electron and a positron annihilate each other into a single photon while conserving energy and momentum. They can annihilate into 2 photons, because 2 photons, they're both moving at the speed of light, but in different directions. So the center of mass of the 2-photon system can still be moving at 0 speed, or whatever speed the electron and positron were moving at. Okay. That's why we didn't do that, and that way of thinking is very important for what I'm about to say here, because there is an implication of the fact that energy and momentum are conserved. So what we can do is we can sort of complicate our diagrams a little bit by drawing little arrows for the momentum, call it P1, and energy, E1. This also has momentum, P2, E2. For particle 2. This is particle 3, so it has momentum P3, energy E3. particle 4 over here has momentum P4, energy E4. And so this is why Fineman diagrams get complicated, because you see the arrows representing momentum are separate from the arrows representing electronness or fermion number. But okay, the point is, at every vertex, the total momentum and total energy are conserved in a Fineman diagram. That's part of Feynman's rules that he made up. So here you have a certain amount of energy and momentum, which I could write in two different ways, which are equivalent to each other. So when P1 comes in, it splits into the momentum coming down. Let me just write this as P5 E5. And the point is that P1 equals P3 plus P5. And likewise, E1 equals E3 plus E5. And that's because at this vertex right here, P1 splits. It goes partly into P3 and E3, partly into P5 and E5. And then that P5 and E5 recombine, so we have P5 plus P2 equals E2. Nope, equals E4. What am I doing? Clearly missing my brain now. P4, that's what happens at this diagram, and likewise E5 plus E2 equals E4. Okay. And that actually is enough to fix what E5 has to be. If you add these equations up and check, you'll find that everything is consistent. But energy and momentum are related to each other, right? For a massive particle, or for any particle at all, there's a relationship. The energy squared equals the momentum squared plus the mass squared, okay? You can't separately decide what the energy is and what the momentum is. These quantities, P5 and E5, will not obey, in general, this relation. The energy is just whatever it has to be to satisfy energy conservation. They will obey this. So this, these, yes. This, no, for E5. This is not true for E5, okay? So we have a way of saying that. What we say is that, we use yet more colors, sorry about that. We say that these ingoing particles, this whole bit here, and the outgoing particles, this whole bit here, these are real. These are real particles. It means exactly what it means. All the ingoing particles you can make, right? You can create some electrons and some positrons, put them in. The photons coming out, you can detect, right? They're certainly real. They're what you see in your detector. But the intermediate stuff, the stuff in between, okay, the particle that is neither coming in nor going out, that has a name. It is called a virtual particle. And virtual particles, here's the sort of big reveal, virtual particles aren't really particles. Virtual particles are a way of talking about the vibrations in quantum fields. What's really happening here is a vibrating electron field and a vibrating positron field, two different wave packets, are coming together, and when they overlap, all these other fields start vibrating along with them, the photons, the electrons, etc., in different complicated ways, and then something goes their merry way. So this is why, in practice, quantum field theory is really hard to get right and to get rigorous, because we understand what the particles are doing when they're far away and not interacting with each other, both before we start and after, but when they're on top of each other, the math becomes very, very difficult. The Fineman diagram language says that we can think about what happens in between as if it were a set of virtual particles, but these virtual particles do not move at the right speeds. They do not have the right energies. A virtual photon is not massless. The energy of a virtual particle is not its momentum squared plus its mass squared. In fact, the energy can be anything depending on just making energy conservation come out right. So they're not really particles, but they're a convenient calculational device. That's why I say a Fineman diagram is a story. There is a true story, which is what is the amplitude for a certain reaction to happen, but the intermediate steps are a calculational device. You kind of know that has to be true because the real process that you're looking at is the sum of all of these different diagrams. And all the different diagrams have different sets of virtual particles in them. They're not exactly the same. So Feynman actually, so anyway, but that is the way of thinking about Feynman diagrams. They're calculational devices for doing calculations in quantum field theory. I just don't want you to take all of the steps along the way overly literally, okay, including the virtual particles in between. Now, I'll reveal Feynman, when he was inventing this, he had an aspiration. He was hoping that he was not coming up with a set of calculational tools to do quantum field theory better. He was hoping that he was replacing quantum field theory with a good old-fashioned particle theory, the theory of particles that be created or destroyed following the rules of these Feynman diagrams. Turned out not to be right. Again, many missteps along the way to any great idea. And it turns out this is a way of thinking about quantum field theory, not a replacement for it. Part of his motivation was the cosmological constant problem. Remember, we talked last time about the fact that when you have fields pervading the whole universe, these fields have energies, and the energies can be added up, and if you just do it naively, the quantum mechanical contribution to the energy of empty space is infinitely big. And this is one of those things that physicists have known for a long time, but before around the 1980s, they didn't worry about it that much, but some people did. So Feynman worried a little bit about it. Philip Anderson worried about it a little bit for different reasons, but they thought that this was a problem with quantum field theory, right? That it gave an infinite energy density to empty space. If you could replace the fields with particles, you could get rid of that infinite energy. It didn't work, so we are left with both this wonderfully accurate calculational device of quantum Feynman diagrams and this somewhat unnatural formalism of quantum field theory. We don't know what to do about that. I'm not going to reveal what to do about that. We still don't know what to do about the energy density of empty space, but we're thinking, and it might be that we do, in one way or the other, have to replace quantum field theory. But in the meantime, it is absolutely the best way we have of understanding nature currently available.